industry nowadays for graphene. But I am also a visiting researcher, not a professor. I am a researcher at São Paulo University on the laboratory of Tribology, that is called the LFS, which means Phenomena of Surface Laboratory. So I have worked more than 30 years at the Mali Tech Center, mainly for piston rings, cylinder liners, oil, etc. As I told you, I also am visiting research at São Paulo University, where I did my PhD and several postdocs. I also spent some time at MIT, Massachusetts Institute of Technology, and in France. So I am a kind of hybrid between industry and academia. Today I will concentrate more on some theoretical points. It will be very briefly for time reasons, so I will try to give an overview, but I cannot go deep in the details. To the ones that have interest, most of my presentations and papers are on my ResearchGate. So this link here, you can download my presentation, most of my papers. So I will try to talk maybe for 1 hour or so and try to answer questions later on. So the ones that have questions, please try to put the number of the slide, because this will help me to later on to return and try to answer the questions and write on the chat. PDF copy of this presentation will be distributed to the ones that are interested, so later on you can visit, okay? So what I will cover today is, after a brief introduction about combustion engine and tribology, impact of CO2, that nowadays is very important, a little more details about engine friction and the CO2 impact. As I told, especially in Europe, this is very important topic. There is a lot of talking and investments on electrification. Then I will go a little more detail on the lubricant regimes, oil viscosity, roughness of the parts in the engine, especially the cylinder liner. A few words about computer models, and something that I have started to work less than 2 or 3 years, that use of artificial intelligence models to predict fuel consumption. Okay, so we start for introduction. Well, there is a lot of tribological parts in a vehicle, say from the engine, gears, brake, etc., etc. Most of the cases we wanted to reduce friction. Of course, brake and transmission and the clutch at least is an exception. What I will talk today is mostly about the engine tribology, piston ring, cylinder bore, but the concepts about roughness, lubrication, etc., is most of the cases valid for the other components. So to the ones not directly involved in engine, maybe some value on look on the fundamentals, because the same thing apply for other components. Okay, so for tribology, most of us engineers, we work looking for the system. We wanted to improve the performance, to reduce the wear. We have longer durability. So this is usually a scale of meter or millimeter. If you go to component, then we want to calculate the torque, loads, vibrations, clearance to assemble and under working, and etc. For tribology, that is the study of friction, wear, and lubricants, we needed to go smaller or see in more details what happens between the surfaces. For example, can be a piston ring, a cylinder liner, but can be a bearing versus the crankshaft, and can be even your shaving against your face. Okay, we are not going to cover nowadays human tribology, but that is of course. So on the micrometer level, we pay attention, tribology pay attention to the contact. So asperity contact, elastic hydrodynamics. I will say a little more on that ahead. Wear, pitching, scuffing. We pay attention to the asperity. So even surfaces that appears to be very smooth, if you pay attention or if you look in detail, you're going to see there is roughness, and there is a strong influence on the tribology. And then if you go to the nanometers, Then also to see the trade-off. Most of the oils have additives, anti-wear, and friction modifiers. So also this is important, although very difficult. This is still, let's say, few universities works really on modeling of ribofumes. And if you go to sub-nanometer, then there are so-called nowadays 2D materials, and graphene is one of example, is also my current topic of work, but this is too detailed. So nowadays, today we are going to go around between micrometers and millimeters, okay? So if you take any component that is even rotating or sliding, you can say piston ring versus cylinder liner, or bearings, or an electric motor, the exo, or so on. Usually we have the inputs from engineer perspective: geometry, speed, load, materials, lubricant, temperature, and ambient. And from output, from the tribology perspective, we wanted to model, calculate, measure, eventually reduce friction, wear, then I would say about idle and asperity pressures, but also there is also noise, failures that we needed to avoid, or so on. So if you take an example of a rotating bearing, typical component for most of the machining, not only in the engine, but any machine also that has rolling bearings. Then there is a rolling against the racing, the external ones. And if you really go to the details, and this is the subject of a study for tribology, we are going to calculate what are the pressures that are appearing here, what is the oil film thickness that separated the parts, that are very, very important. If you try to run dry, most of you know that the component will not survive. So we really depend on the lubricants or so on. And to ones that are not experienced, let's say, the oil film thickness separating the surfaces are in the order of 0.1 to maximum 10 micrometers. To give an idea, the diameter of our human hair is between 50 to 100 micrometers. So we are studying things that are sometimes 1,000 of times thinner, the oil film thickness. Okay? Talk just a little briefly about the laboratory that I work on the university. Remembering again that today I'm talking as a university researcher and not as an industrial researcher. So there we have, let's say, characterization tools, equipments to measure the surface and so on. So really pay attention a lot to the roughness. We do a lot of modeling and simulation. I will show some examples later on. We, of course, as most of tribology, we do a lot of experimentals and tribal tests, spin on disk, SRV, and so on. And we also do courses and lectures as I'm doing today. We have a strong collaboration with the automotive industry. I come from the industry, so I started to interact with the university laboratory from the industry. So I will not go in details, but you can see here a lot of automotive companies as Ford, General Motors, Fiat, and so on, and also some universities in Europe. For example, the Valencia University. I needed to now to include your logo here, and so on. We have a very large project. It was 5 years. Here we have maybe 3 or 4 when we created several computer models that are available for university use, so in case that we want to later on that details. And we published several papers and several PhDs together with the universities in France and Europe and Germany. What we are looking is to reduce the CO2 emissions of engine components or combustion engines by 20%, doing that by reduce the friction. And for that we need to, and I will try to cover today, something about low viscosity oils, coatings, and surface finishing. And currently, and the next years, we are going to dedicate more efforts to graphene. Graphene is a very novel material, and they have some very interesting properties, not only for electricity, but also for tribology. But I will not cover this today, can be topic for another lecture. Okay, as I told, the idea is try to cover a little from laboratory to industrial or real application. So very common nowadays is to use what is called a technology readiness level, TRL for short. This was created by NASA some years ago. So he tries to divide a given project or a concept from idea to basic research, technology formulation, small prototypes, then demonstrations, then really production. So usually at the university, what we can try to concentrate on the first steps, let's say to do some basic research, very detailed computer models. So nowadays, today, I will give more details of what was done here, but in most of the cases, the concept that is showing, and I show some examples, are rich commercial application. But this, of course, was done at the industry, and there is a lot of manufacturing details, commercial ones that I will not cover today. Okay. So moving to engine friction and CO2 impact. There is, as you know, a lot of discussion about electrification. So some people consider that electric vehicle has zero emissions. This is not true. Let's say the car can emit no emissions, of course, it's electric. But to produce the electricity, to produce the car, you are already creating or producing CO2. And also how much is the impact depend of your electricity grid. So this is a very nice paper from this year from MTZ. MTZ is a famous German, but it's English version for dedicated to car that compares, if you take the electrical grid average, Europe 28, 28 states, countries that are on that, how much would be impact of electric vehicle compares with the gasoline one and a diesel one, combustion one. So in average in Europe, the impact would be 45% or say 55% reduction of CO2. But this depends on the how electricity is produced. So from the same sources, like rotation in Poland, for example, the reduction will be only 17%. And this after 200,000 kilometers. So if you buy a new electric vehicle, probably for the first 2 years or maybe 3 years, you are producing or you have produced more CO2 than if you buy a combustion engine. And this is from Audi. References here, the one that want to check the details. But also, in my opinion, a big problem is our trend to move to larger and larger SUVs, for example. So in this case, data from Audi shows that if you buy, if you are rich enough, I am not, a large Q7 electric vehicle, indeed you are producing more CO2 along the life, 200,000 kilometers, than if you buy a combustion engine A4, okay? And especially until 100,000 kilometers or so on, if you compare, this is the A4, and let's take the Q7 Europe. So most of the cases you are consuming more, producing more CO2. Even if you move the electricity to a greener version, let's say hydroelectric electricity, you will still have to run more than 100,000 kilometers to have the break-even, because indeed you produce more CO2 to produce the car, the batteries, and so on. So this, in my opinion, makes important that we still make efforts to improve the efficiency of combustion engines. Combustion engines will live for decades yet, so we needed to improve and reduce the CO2. First thing, I'm not really going into details, this is a little more complicated, but if you look on the references, almost all of them agree that engine friction losses are around 10% of the fuel energy. So most of the professionals and academy, okay, if I zero the friction losses, I'm going to save 10% of fuel. This is wrong, because you spend energy or work to overcome the friction losses only after combustion. And as you probably know, combustion efficiency is only around 40%. So in order to overcome the 10% of friction losses, indeed you have to consume 40 or 25, sorry, energy. So indeed, if you can zero, this would be very difficult. But for example, if you reduce by half the friction losses on the engine, we are going to save not only 5% of fuel and producing 5% less CO2, but 12.5 again, because you needed to consider the combustion efficiency and friction losses occur only after you have converted fuel energy to mechanical energy. In terms of friction reduction, so if friction reduction is important to reduce fuel consumption, CO2, we needed to pay attention to the components that produce more friction losses. And on the combustion engine, about 50% is produced by the piston, liner, and ring. Okay. You can visit this slide later on, but I would like to remember, okay, we wanted to reduce the friction, for example, on the piston, by increasing the installation clearance to reduce the skirt roughness, to make some short skirt, but, and very important, we need to keep the durability. If you increase the installation clearances, maybe you have problems of noise. So in all the cases, we have to make compromises in order to reduce the friction and wear, but keeping the good performance of the engine. Okay, the same for the ring, for example, is relatively easy to reduce friction losses if you reduce the tangential load of the ring, but there is a risk of increasing oil consumption and so on. As an example, this is a Brazilian one that we did in 2013 with the computer models that I will show a red one. So this slide is more to motivate you. Later on, I give more details how we run the computer models. We estimated that by improving the components, we can reduce the friction by 12%. And for a given engine, we can reduce the fuel consumption by about 2%. So we went to the OEM, the car manufacturer, presented the working on modeling, etc., asked for the engine, and 6 months later, with the improved parts, the car manufacturer measured not 12, 21%, much more. Details I will not cover today, but are some reasons of that. And fuel savings at the stage, the same order that we have predicted. FTP is the urban transient cycle for emissions in North America and also in Brazil. So we got 1.3 and 2.3. So the customer was very satisfied with the results. Here are the savings on the complete engine map, the speed by torque. And also here are the transients in terms of RPM and torque of the engine, because this, to the one familiar, these emission transient cycles are very complex. So on that time, we are very, very happy to be able to simulate, to predict, and to obtain the results. Because again, let's say, the good things about model is that you spend relatively little money in order to find potential good solutions. And only after that, you go to produce the parts and to make more expensive costs. One interest, this was also published in English in a Brazilian Congress. Moving to lubricant regimes, oil viscosity and roughness. I used to say that if you wanted to understand tribology, the first thing that you need to learn and to understand, really understand, is so-called the Strebeck curve. Okay, any tribology book and so on will tell you about that. But in my opinion, not everyone really understand how to read this curve. And as I said, it's very important. What are these Strebeck curves try to say to us? That the friction, the center of friction, depends of the separation between the parts and divided by the roughness. So AGM is the oil film thickness, and sigma is an indicator of the roughness between the parts. So if you have a relatively thick film, you are in complete hydrodynamic situation. So there will be no boundary friction, means no contact between the parts, so no friction. This is the red line. But if you increase the speed, you are going to increase the friction because it's hydrodynamic. On the other hand, if your load is higher or your surface is rougher, you enter, and this most of the components work on this regime, the so-called mixed, when the friction is a combination of the hydrodynamic and the asperity one. And if you really go to very high loading or very low speed, and then you have a strong contact between the surfaces, then oil viscosity is almost no dominant, and you face a risk of wear and scuffing. So usually the books show this, what is called a film parameter. Again, is the oil film thickness or the separation between the parts divided by the roughness. But for us engineers, it's also important to understand that this same plot or curve is related to speed, viscosity, and load. So if you have a given component, like a piston ring versus liner or a rotating bearing, if you increase the speed, you are going to move to more hydrodynamic regime. If you use an oil with a higher viscosity, you also go to more hydrodynamic. The opposite, as the trend nowadays, to use lower viscosity oils, then maybe you move from hydrodynamic to more mixed. And if you increase the load, you also moving from hydrodynamic to mixed, or eventually mixed to limit. So you know, for example, if there is overload in a given equipment or combustion engine, you have a risk to have scuffing or very severe wear. This plot is from Shell, and they tell what are the components, engine components, where they work. So let's start with the plain bearings. Okay, speed is relatively high there, and they work mostly on the hydrodynamic situation. This is the reason that if you know that the bearings, they have a relatively soft material because they don't depend. The same for a skirt. Most of the piston skirts are with aluminum, with some maybe graphite coating, and after 2,100 kilometers, 100,000 kilometers, you will still see very little wear on the piston skirt. Piston ring, as is a reciprocating and load is much higher, they go from hydrodynamic to boundary, especially at the top of that center in the moment of the combustion, the explosion, especially the top ring suffers a lot. So we have to use very hard coatings for the piston ring and so on. And the valve train, because it's a very localized contact, it works mostly on the boundary and mixed, and also they have to have a very good surface finish, right? Don't try it, but if you do a rougher cam follower, you're going to see that wear and friction will be terrible. And in terms of oil, as this is hydrodynamic, viscosity of the oil is important here. So low viscosity oil will move to the mixed regime. On the other hand, when you have a strong contact, then there are the oil additives, especially ZDDP, that is the common one to wear, and friction modifiers. Molybdenum is the typical one that you can find, and engine oil. So this is also very important because when you are planning to study or to run a model, you need to pay attention. I say it makes no sense to use boundary and mixed models for plant bearings and skirt because they work on the hydrodynamic. And the opposite is true. Piston ring being one of the more difficult because they can have from the boundary to fluid hydrodynamic. I will talk a little more later on that. Piston system are very complicated system because it's transient. The combustion pressure, as you know, goes from almost atmosphere to nowadays 220 bar or even higher for heavy-duty diesel. There are temperatures, so the components, take example of the piston, due to the thermal deformation, they change the profile and dimensions from the drawing. This is an example. The piston is hotter on the top, so it thermal deforms more, so it creates things like that. Also, if you take the engine bore, the regions between the bore is more difficult to cool, so usually the temperature here is worst or is higher. Cylinder topography is very important. I will mention some words ahead. And oil properties, and especially the viscosity, and the viscosity is very dependent of temperature. This plot shows for a given oil viscosity how, let's say, for 30 Celsius degree, I think that in Poland you can even have lower than 0, oil will be very viscous, but when you go to 100, 120, it goes very low. So in order to understand this and to improve the system, you really needed to understand. And also there are other effects, as I told, there are transients, the parts we wear, there is oil degradation. So this is an example. This is the profile of the top ring as new. Right? The manufacturer will produce a very nice barrel shape because it's good for hydrodynamic. But after, in this case, 750 hours, the wear create a taper like that. So also, if you want to understand, for example, failure in the future after hours and hours, or be careful not to use the profile of a new ring because it will be not. Also very important for the people that investigate tribology. Most of the cases we pay attention to the coefficient of friction, the ones that you can find on tribo test that I show later on. But for fuel consumption, friction losses are relevant. Friction losses are the force multiplied by speed. So in this case, it's the friction measured along the 4 strokes of an engine using the so-called floating liner. There are a few in the world. In Japan, German, and Brazil, we have one. They can measure the friction at each creep angle of the piston versus the piston ring. So if you look just the forces, you are maybe trying to pay attention to this peak here. That is the maximum friction that occurs just after the combustion. But if you are preoccupied in fuel consumption, this is not very important because here the speed of the piston is very low. So the same data, if you move to friction losses, energy, you're going to see that close to the top dead center or any reversion points, the friction losses, again, the energy will be almost 0. So mid-stroke will be more important to find fuel solution. So if you wanted to understand wear and scuffing, then you need to pay attention to the top dead center. But if you wanted to save fuel, reduce mid-stroke and the speeds, so the power is higher, friction losses are higher, you need to pay attention to the mid-stroke. This combination is not trivial. It's complex, but it's necessary if you want to save or if you want to solve both friction wear versus the fuel consumption. Going to some real cases now, okay? Most of the car vehicles in Europe and Japanese now use what is called thermal spray. So instead of the cast iron, that is still common on heavy-duty diesel, they are using aluminum block, but with a coating of thermal spray. Different car manufacturers use different solutions, eventually similar but different names. So some of them are called PTWA, LDS, this mainly Daimler, BMW, and Nissan, and it's very smooth. If you see, very, very different from the normal recast iron honing. I will give a little more details. It's so smooth. This is a real photo, and there is a paper on the top. So this is the reflection. So this is the reason that it's called mirror-like. Here is another photo, also from this case from Nippon Piston Ring and Hino, that is a Japanese, in this case is a diesel engine indeed. So you can see the reflection of the hand of the guy. Okay. And this, I will say a little more on that because it's a very top, let's say, hot topic to investigate nowadays and needs some special attention. And also, as you know, more and more the industry is moving to low viscosity oils. In Japan, Honda, for example, is already using 0W8. And this plot, also from another source, is not mine, compares the viscosity at 100 Celsius degree, and also what is called a high temperature, high shear screen. Sorry. High temperature, high shear viscosity is 150 Celsius degree, but with a very high shear. So the oil viscosity becomes lower. And if you see that, let's take 0W16, okay, that Europe is already using. This may be 2 times more viscous than the diesel fuel. So this is very good for fuel saving because you have very little hydrodynamic friction losses. But as you can expect, there is also problems of contact. Okay, I will start to go a little faster because I'm spending some time. In most of the research groups, when you wanted to optimize cylinder optimization, this is the way that we do at São Paulo University. We start with actual cylinder bores or prototypes. We do very detailed topography measurements. Then we go to rig tests, modeling, and finally go to engine model. These approaches are not only academic. Here I reproduce papers from the industries about the same topic. So, for example, from Audi, from Daimler, and so on. Very, very important. I told you that Streetback curve is, in my opinion, the first and the more important thing that you need to know about tribology. And if you remember, roughness is important to understand because the Streetback curve use oil film thickness divided by roughness. But most of the people use area zeta or area as indicative of roughness. And I consider this very risk, to not say that is wrong. Why? Because both area and area zeta do not differentiate a peaked surface versus a valid ones with valley. So these two surfaces have the same value of area, and you can imagine that you have a part slide here. This will have a lot of contact and wear, and this probably will be very good. So area and area zeta are not enough to describe roughness in most of our components. So please use at least the Abbott curve. This was developed by Volvo decades ago, and that they use 3 parameters that is called RPK, RVK, RVK. That is indeed the ones that describe or quantify the peak heights, the valley heights, and what is the middle, that is the core. So I don't have time today to cover that, but please, please do not use REA if you wanted to investigate tribology. You need at least to use RPK, RVK, RVK, that most of nowadays roughness equipment can measure without problems. This plot shows different cylinder honings from the standard plateau. This is for heavy-duty diesel. I will show you next one, the ones for mirror-like. And this plot I usually to represent, sorry, these are very in the color here. This dark blue is the RPK. So I like this plot because it separates what is the valley, what is below the surface, and what is peak above the surface. Okay. Going a little about computer models, as I said, more and more engineering universities and industries are using computer models because they are cheaper and usually allow us to investigate things that will be very, very difficult to investigate by tests. But it's always the question, how complex or how comprehensive would be your model? If you wanted to simulate, for example, the complete engine, or if it really goes to the fundamentals. So a good approach is usually to understand which problem you want to solve. If you want to solve or improve roughness of the cylinder, maybe if you run a simulation on the engine, it would take forever, you need a lot of data, etc. So usually it's better to start from the fundamentals, as I try to show later on, and with more and more move to the complete engine in order, for example, to know how much would be the durability, how much would be the consumed fuel saving. So how to look on that is key to have a good approach. Okay, the same for tests. For example, you can make the car tests. This will be very expensive and with a lot of variation because you depend of your driver, the gasoline, and so on. You can do engine test, you can do component test, or if you go to the fundamentals, for example, a simple pin on disk. Again, how to choose this depends what you want to solve and how you are prepared to spend. And this I showed before. Let's say if you go really to fundamentals, it's good that you have some computer models to help you. And I will show some examples. And this plot is very detailed, but again, most of the people use what is the classical model, that is use the Reynolds equation and Greenwood trick for asperity contact. Nowadays, we have much more sophisticated tools for that. I'll let this slide later on to the ones interested. Most of the cases I run nowadays, the what's so-called deterministic one. An example, this was published in one of my papers and compare, in that case, the car manufacturer was changed the gray cast iron cylinder bore with a sliding honing. Slide is relative smooth honing and are moving to a mirror-like coated bore. And this shows actual measurements of the surfaces. Pay attention to the scale. So this goes to 1 to minus 2.5 micrometers, but this one goes only to 0.1 to minus 0.04. The ones that receive a roughness measurement, one of, let me call problems, is that the roughness equipment will increase the scale to show the roughness. So if you receive a measurement of the Greek iron versus the one mirror-like, you may, on the first glance, even consider this is rougher than this one, okay? But then I put in the same scale, so the same scale here from from 1 micrometer to minus 3, then you note how smooth is this new surface, okay? The same on that. Then also you need to pay attention to waviness. Usually your roughness equipment filter the waviness, and for most of the cases, this is not a big problem. In this case, I compare for the sliding honing, the amplitude of the waviness, this SWT, is around the order of the SA of the roughness. But you go to the mirror-like, because SA is much smaller, you see, almost 10 times lower, waviness become important. So waviness in this case is 10 times higher than the roughness. So if you neglect the waviness, you can risk to have problems. This also is covering more details in some of my papers. Also, this is every time I tell you, I say, don't trust on photos and reports. Try to see the real part, especially these mirror-like surfaces can easily make you be wrong. Take this example, okay? Suppose that this is a surface of a given machine or combustion engine equipment. It's not, I will show later then what is that, but most of the very nice finish. Okay, you have a plateaus, some valleys here to receive the oil. So most of the tribological guys will be happy with this kind of surface finish. Again, you have a area for plateau, a smooth one that can support the contact, and you also have some valleys and dimples to serve as oil reservoir. But what do you think about this one? Appears very bad, yeah, very rough. So if one needs to choose between this surface finish and this one in red for low friction, low wear, most of the people will choose this one. But if I tell you they are the same, it's just rotated. You see? They are the same surface, but our brain is used to think that the light comes from the left. I don't know why, but this is not tribology, but we think. So when you see shadows here, you think that this is a plateau. And I will return again. Same picture, same photo. I just rotated that. Okay. You are going to think that this is a rougher surface. So I make some mistakes, to be honest. Indeed, I went to study this because in the past I make some mistakes in that surface was with protuberances and indeed it was with the dimples or vice versa. I will go faster into the details, but we at the USP and that time also together with Mali, we have developed some relatively simple codes when you can use to simulate, for example, piston ring versus a cylinder liner. Academic version is available to the ones that want to try. So you put, as I did before, as input velocity, are the pressures, boundary coefficient, and so on. And then they calculated to you what are the hydrodynamic and the asperity contacts. Again, hydrodynamics are the ones produced by the oil, and asperity is one by the contact, the material contact. And in this case, I compare the same case. It's a piston ring move at 1 meters per second. Let's say it's maybe half between the top dead center and the mid stroke. At mid stroke would be around 10 meters per second, or depending on the engine. For 100 Celsius degree versus 40, you see that at the 40 Celsius degree, because the oil viscosity is higher, you have a much higher pressure. Sorry, here is a mistake here. There is some colors problem. I will skip. But believe in me that when you increase the viscosity, you have more hydrodynamic pressure and less asperity ones. On the time, there is a paper that we published, this one. We investigated several oils, different oils viscosities on the Tribo test, is a ring versus liner. And at that time, nowadays is considered, but at the boundary conditions, if you decrease the viscosity, you increase the friction. This is not trivial, but believe on me. And then we run the simulation, we are able to predict some things. And when we put the viscosity as in this Trebek curve, but it's nice to see that all of the cases joined to our same curve. There are effects of friction modifier. As I said, one of the oils we run, or we have a formulation without and with friction modifier. Friction modifier was able to reduce the friction on the boundary mix regime, but when you increase the speed, it goes to the hydrodynamic. So then there is no influence of the friction modifier because there is no contact between the parts. Also, there is contact, sorry, of the low friction coatings, DLC, for example, diamond-like carbon, but this usually you needed to go to experiments. There are a few models nowadays that they can can deal on that. And this case shows also a paper. This was published by a colleague of mine at that time. At Germany, investigated diamond-like carbon rings with reduced oil viscosities and seeing what was the scuffing resistance of that. So TOC was very resistant, very high resistance to the when we're using low viscosity oil. And we also making tests on engineers. This is another paper indeed for a colleague of mine that is Polish grandfathers, comparing the wear on the chromium nitride PVD versus the new TLC ring coatings. There are very good commercial codes. So the ones that I show you are academic, relatively simple, but pay more details, more attention to the details. But one that several companies use and are also using is the AVL Excite. So you can model almost the complete engine and even the car. So you can investigate the noise, vibration, and so on. This is usually the car companies have license and people training to do that. At the university, we try to collaborate with AVL, running some more detailed cases, not the complete engine, but more detailed ones. We have published some papers. I will skip the details, but I call attention, let's say, the oil film thickness calculated by AVL of a Greek cast iron versus that mirror-like. And if you see the oil film thickness goes to 0.1 micrometer thickness. This is, if you remember, is 1,000 thinner than oil film thick. Sorry, that human hair. This is how the cars are running nowadays when they have such mirror-like surfaces and working well, if you know. A little more details. I will skip it. This is too detailed. I'm running out of the time, so to are safe. But we calculated the friction losses. So on that case, at least, just reducing the oil viscosity, you decrease the hydrodynamic friction losses, but you increase the asperity one, as predicted by the Strebeck curve. So indeed, at least for piston ring, there will be no advantage of reducing the oil from 10W40 to 0W20. But if you go to smoother surfaces, then you have a big saving. So nowadays, the main messaging, and we have published several papers on that, let's say, you need a combined approach. If you just reduce the oil film thickness, or sorry, the oil viscosity, you may risk wear and asperity losses. If you just use the mirror-like but keep the same oil, probably you are not benefiting from the more expensive surface finish that you use. You need to use both, as the car companies are doing, let's say, smoother surfaces combined with the lower viscosity oils. Recently this year, we also published in collaboration with Valencia University papers, in this case, using the not only simulating, doing tear-down engine test. So you are going to measure the friction losses of the different components, the bearings, the piston assembly, the valve train, for different oil viscosities, and see that there is an optimum in this engine, at least for 0W16. If you reduce even more the oil viscosity to 0W8, you are going to increase the friction losses. You reduce for bearings because they are still working on the hydrodynamic, but in this case, you increase a lot on the piston assembly and especially on the valve train, that you should remember are the ones working on the mixed and boundary regime. Then we investigate for several cases, different velocities, different oils, and so on. I will skip that, but the paper is interesting in my opinion. And we also predicted the wear, so the mirror-like, because they almost zero the asperity contact, are able to reduce a lot, at least by simulation, the ring wear. Going to my last topic today is the artificial intelligence. If you know, let's say, all the industry, but also the banks, medicine, all the areas are using, especially the machine learning models. I say a few words on that. I'm not really an expert. I'm still investigating and make using that, but I see a lot of benefits. So basic artificial intelligence is what we call it when the computer do things that we usually associate with the human intelligence. It can go to expert system, Google Translator, for example, if you see robotics. But what I'm trying to use with relative success is so-called machine learning. Machine learning, we use artificial intelligence tools on very large data sets. Okay? And then we feed the system, the algorithm, with that large data set, and usually experimental, but can be also modeling, and ask the system to tell us what are the understanding and especially the predictions. I will try to show some examples. So especially for transient emission cycles, this again is the one used in North America and Brazil, but European is relatively similar. And if you take what is called the real drive emissions, you have even more complex. So this is the speed along the time. The cycle usually is divided by cold phase and hot phase. And only the cold phase, a given test, produce almost 14,000 data points. Okay. Speed, load, change of your temperature, and so on. So if you try to analyze by yourself, it will be very complicated. So in this paper that is going to be published still this year, we use both a tribal model, that I will later on a few details, but especially we use the machine learning. On the paper, we use data that is available from organization in the United States. It's called Argonne National Laboratory. So the ones interested, they have very large public database on emission cycle. So we use them to publish for 3 different vehicles. These are the vehicles, again, from that database. From the tribal model, this is the measured value versus our model. And you see that for most of the cases, we are able to make very good predictions, what would be the fuel consumption. Few cases usually are the old ones. The engines are not going to detail, but indeed for the later on we abandon such case. But for most of the cases, we have a good correlation. So these are only the cars with the gasoline direct injection. So we have more detailed data from the test. I say to use the machine learning is good that you have a lot, but also good data, and you have a very good correlation between what was measured on the transient cycle versus our prediction. And then it's too detailed, I will skip today, but believe me, we also use that one that I showed was so-called tribological model. It's more, let's say, theoretical base. This one is pure artificial intelligence, and especially using what's so-called random forest that make decisions. I don't have time to explain details that, but when you use these are the fuel consumption in each point, okay, and the blue one is the measured one, and the orange one is our linear model, and these are more sophisticated random forest. So especially with the random forest, if you see, we are able to predict the instantaneous fuel consumption with very good comfortability. So nowadays we are using for other cases. I will skip that. I think this one summarizes. So we are being able to predict it. Let's say what. Sorry for being fast. Really, this needed a specific presentation. But to simplify, we train the machine learning model with the measurement at the cold phase. And then we use the model to predict how much would be the fuel consumption at the hot phase and the highway and other test cycles. And current models that we are using are being able to predict the fuel consumption with an error of 2%. what we consider to be very good. So when with much less information, only the cold phase, we can predict the fuel consumption at urban, hot ones and highway in 2%. Indeed, what we want is to use the model to predict, say, what would happen if we reduce the oil viscosity and so on. So after the model is being trained, we can start to make questions to the model, especially for transient emission cycles. So this ends my presentation today. I hope that I will be able to answer the questions, and you see values on my my presentation. This I use Google Translator to say thank you and take the chance that we are close to the Christmas, nice Christmas and a happy New Year. I will distribute the PDF, as I said, so the ones that are interested, you can find more details even on my ResearchGate.net page or on these papers on that. Okay. Thank you.
Thank you very much. So we're looking at questions now in the chat. If students or anybody has a question, please put it in the chat, or you can ask directly if you want.
Well, one question that comes from Piotr is the machine learning feasible in engine design, in particular the shape of the piston ring? Are the results great enough? Well, for machine learning, you needed to have a very large data set. Okay. For example, for the empirical one, I think that will be too expensive. But suppose that you can run several simulations, input on the machine learn, and then predict what would happen with a given one, or to ask them to propose optimized designs. Okay, but my opinion, I will not use that. Usually it's good when you have a lot of experimental data, difficult to, suppose that you are on Daimler or Volvo, so on, and you have thousands and thousands of measured parts after field test, and some of them failed, okay? And then if you feed all this information in a good machine learning, maybe or probably, you'll be able to find what are the profiles that cause the problem, or when the problem occurs, what are the profile. But for the piston ring, I know that you mean profile, because free shape is different. I will not use that because, again, for machine learning, usually for artificial intelligence, it's better that you have a lot of data, difficult to be analyzed by a human being. Okay.
Panie Grzegorzu, może pan zada pytanie, bo się zgłaszał pan.
Yes. Hello, my name is Grzegorz Koszałka. Very nice presentation. And in one of the slides, you show the results of simulations for low viscosity oils. And in these simulations, the share of viscosity friction was extremely low in comparison to asperity losses. I don't remember, but there was a bar.
Probably yes. This one.
Yes. In this slide. And do you think that in real engines such, well, because that means, as I understand, that in the whole engine cycle, there is mixed lubrication, yes?
Yes.
And how about wear in such conditions?
No. It's good questions. And if you remember one, let's say, you needed to differentiation friction losses, and friction losses would be the friction multiplied by speed of, in this case, piston ring. So it will occur mostly at mid-stroke. But if you take the wear, although the speed is low, pressure is higher. So in this case, it's friction losses. And it's dominated, in this case, depending in asperity. If you see, let me try to remember, because we are in a relatively low speed, and there is a relative half surface, okay? See that when we move to a very smooth one, then we almost zero the asperity pressure. This again relates to the Strebeck curve. If you have a rough surface, then you'll be contact. Have a smooth ones, then will be little contact, and then most of the friction loss. See how changed it from the height here. So at a relatively high viscosity, 0W20 in this case, there is almost no hydrodynamic, but a lot of contact. Yeah, this is, sorry, because here I am comparing the roughness, but with a rough surface, there is a lot of contact. With a smooth one, we move from left to the right on the Strebeck curve, so almost disappear the contact, but then we have increase of hydrodynamic. But the total is still lower than in this case. Not sure if I was able to answer your question, but I say this is as good as we can do as a simulation from a real case. Details on the paper I can send you later. But all the time, please pay attention that when we are talking about friction losses, you are more on the mid-stroke, because then the speed is higher. And if you go to wear, that we try to simulate in another case, then top dead center, especially reversal ones, will be more important. Okay. But again, all the time, it's good that you remember about the Strebeck curve, where you are. So for piston rings, you move the complete one. But take it, for example, here you have a speed. When you have high contact, the speed will be close to zero. So power energy, that is speed multiplied by load, will be almost zero, although you can have wear and it's even scuff in this case, but when you consume a lot of energy to overcome the friction loss, so fuel consumption would be more on the hydrodynamic. And let me see. And again, I think that this plot shows you the very important difference. In this case, for example, we are comparing a piston ring with a normal coating. In that case, if I remember right, would be gas nitride steel versus one with a DLC coating. And you see that here almost no difference, but at mid-stroke, the DLC produced less friction loss. So at the end, we have a very nice benefit in terms of friction losses and fuel consumption, use the DLC, but not because of the reversal point. This was published, sorry, this was DLC coated liner, okay. It was published again. In any case that you want more details, I can supply everything that I showed today is public and probably was published. This was from my colleague from Mali, was presented on the VDI Congress in Germany, 2014. And it's actual measurements in this case.
Okay, may I add something?
Of course.
I wonder if in such conditions, because I think I more or less understand Strebeck curve, but what happens if in a real engine, because I understand the results of simulations, but what do you think will happen with real engines if they will work in such lubrication regime? What happens with the durability, I wonder?
Yeah, this is a good question, because on the this I'm showing only piston ring and liner, okay? On the real engine, you have the valve train, you have all the other components that somehow we try to investigate in a more recent publication. This was done together with Boris Muth and the Valencia University. And you see, this is, you have for the different components: piston rings, piston skirt, main bearings, cone rod, camshaft. Okay, so what on my industry experience, if you go to low viscosity oils, you have to improve your surface finish, and you have to use usually a lot of oil additives. So if you take, for example, nowadays the, let me call Japanese like oils, but you can also find in Europe the ones, when I'm trying to find it, you are going to find 800 to 1000 ppm of molybdenum from MEODTC. Okay, so remember this plot, for example. Here, actually, let me see if I have a better one. Maybe this one is better. These are experimental data of reciprocating ring aligner, but you can expect to see similar things in other components. When you reduce the viscosity, this is 0W, sorry, SAE 50. This is a relative old paper on your shoes, very. And if this one is 0W30, so we have much more friction at boundary conditions, not in hydrodynamic, but on boundary. So if you just reduce the oil viscosity, probably you're going to face more wear and even risk of scuffing or catastrophic failure. So what you can do is to use oils with more additives, and nowadays the oils are using. So this compares, for example, the next one, sorry, this one is plus is the one with friction modifier. So green versus magenta are the same viscosity, but with more friction modifier additives. Okay, so when you increase the speed or reduce the load, more and more you move to hydrodynamics. So then the additives, at least the ones so-called string pressure, will not have effect, because here you dominated by the viscosity. So here you see that lower viscosity reduce the percent of friction, but on the boundary is the opposite. So in the rearrangement, if you just reduce the oil viscosity, probably you're going to face a lot of wear. What are the industry and what I suggest you to do? First, improve the surface finish. Go to smoother and smooth mirror-like surfaces. The other one, use oil with more friction and anti-wear additives, as they are using nowadays. I have some specific papers on that I can cover in another lecture. Okay?
Yeah, yes. Thank you very much.
But this is not cheap, yeah. That is a problem. I say it costs money. These new oils and these new surface finishes are usually more expensive to do, but because we want to have lower fuel consumption, especially lower CO2, most of the new, at least the vehicle engineers, but even truck engineers, they are reducing the oil viscosity. For example, this one, also a paper that we did in 2016, we use, we compare two oils. These are heavy duty diesel, compare 15W40 versus then W30, and we increase a lot because the truck company are increasing the interval between oil change for 150 hours full power at the dynamometer versus 500, so more than 3 times. See that if you keep the same coating for the piston ring, for example, they wear almost double. Okay, so what is needed? Either to, in that case, we use a coating with a lower friction and more wear resistance, that in that case was the DOC, or we use more a oil with more friction and wear additive, or we improve the surface finish. Usually in the car or truck company, they do all the things together. They say improve the surface finish, they use oil with lower viscosity but more additives. And the same here for the scuffing. You see, let's say, if you keep the same coating, this is chromium ceramic, very typical of a relative older diesel engines. When you go to lower oil viscosity, this is described by high temperature, high shear, you see that the scuffing resistance decreases a lot. In that case, in order to fail, you have to apply 950 newtons. With the lower viscosity oil, only 300 was enough to create. But the DOC will survive even with the lower viscosity oil. This is another German paper from other colleague of mine. But you are right, let's say, don't do just one thing. If you just reduce the oil viscosity, probably you are going to face a lot of wear. If you just improve the surface finish, probably you are spending money without benefits. You need to do a combined solution. Any other questions? Again, from Piotr, improve the mechanical and the engineering. This is what I just covered. Okay, so do not only change the oil viscosity, you need to improve the other ones. And if the oil temperature is taken into account, yes, usually it is. If you go to the engine, usually you have a separate oil cooling, and most of the truck and car manufacturers, they stipulate how much would be the oil temperature. So they exaggerate 120 or so on. And the worst testing protocols, and when you go to very hot to very cold oil, use a separated, relatively large oil cooling, and then you move from full load oil up to 120 Celsius degree, if I remember right, and then you very quickly reduce the oil temperature and the engine, so you also face problems of cracking the head cover or so on. And if it's a simple test rig, then usually you can easily control that there's some electrical resistance, so you can test at 30, 60, 90, 120, and so on temperature. And in the model, also the model has, it calculates the oil viscosity according to temperature. You put the input of the oil, describe the viscosity. Okay. We still have more 10 minutes according to the agenda. So let's try to give my main messages if I can. So I think that most, maybe some of you, work all the time trying to, let's say, to move from an idea to a full commercial application, okay, or to solve a problem. So usually it's good to understand, let's say, suppose that you have a failure in the engine. If you try to solve this without more small scale prototypes or configured models, so on, you have to very lucky or have a lot of experience because you're going to spend money. It's good to have relatively simple but theoretical fundamental tools, and vice versa. Let's say, don't trust the theories if you don't have empirical experiences. You need to navigate through that. And for combustion engines, in addition to durability, cost, etc., nowadays one of the main targets is to reduce the CO2 emissions in order to compete against the electrical ones and to reduce the global warming. In terms of tribology, I think that we can achieve up to 20% of fuel savings CO2 reduction, which is a lot. If you remember the comparison with the electrical one, in Poland would make the combustion engine to have the same CO2 impact of an electrical one, if you take the complete life cycle assessment. This can be achieved by 50% lower engine and transmission friction losses by improve the surface finishing, by reducing viscosity, for using models and experiments to optimize. But it's really necessary to have a synergistic interaction. Okay? Don't change just one, because so you need to understand the lubricant, and there is a lot of chemistry here, so we need the help of the chemical guys. Usually, I am a mechanical engineer, so there is a lot of chemistry here. And today I'm also investigating graphene. There's a lot of chemistry here. We use low friction, wear resistant coatings. So go to chromium nitride PVD, DOC, the thermal spray, and so on, combined with a surface finish. And this combination usually is not so easy. Take, for example, the diamond like carbon. It's hard like a crazy. So in order to produce a surface finish, you need to improve the surface finish. This is also, let's say, when the theory, the academic work needs to work with the industrial one. A university or a tech center can invent a wonderful wear-resistant coating, but someone we need to produce that. So if it was very wear resistance, it means that we also be difficult to machine that on the plant. So this combination also you need to pay attention. And then in order to achieve that, usually you can start because it's simple, because you can explore things that you cannot yet produce. I do this a lot. Let's say before producing prototypes, I start with some concept and simulation. I can change a number there, even if for the moment it would be very difficult to produce. So we can go from very fundamental ones to the full engineering. Then, as I said, for oils, we need to have a tribochemical expertise and characterization to be able to measure the oil, etc., etc. Then you have to produce sample parts, lubricants, prototyping, surface finish, and characterization. What I call multi-scale approach, it goes from, if you remember one of my first slides, from the asperity contact to the full engine. It's also a combination not easy to do. Most of the people even will pay attention to very small details or on the other hand, to complete the engine, to complete the vehicle. So a multidisciplinary group that combine both theoretical guys with the production guys are important. Guys or girls are important. That usually rig tests are much cheaper, more controlled, and you can do a lot before moving to real prototypes of actual engine and transmission parts, which cost a lot of money to do. And then what I call really full-scale tests is combining the oil, the parts, the surface in real parts. But my suggestion, do not start to do here, because you are going to consume all the money and time before find a solution if you don't pay attention to the synergistic effects of the different parts. And this is what my figure tried to say. Let's say you have a kind of cubic Rubik curve, and if you change just the oil, just one of that, the other ones probably will be wrong. You have to find the right way to make all the colors the same, and then combine lubricants, coatings, surface finish, and operation system in order to have a low impact and cost competitive vehicle, car, truck, or machinery. Say nowadays for bearings, I'm not sorry, for rolling bearings, I also investigate, for example, that the thermal generator, larger reductors, transmissions, and so on. So most of the concept that I show is valid for also other equipment. I cannot say this in Poland, sorry, but again, thank you for the invitation. It was a pleasure and an honor to give this lecture. Hope that you see value in what I presented.
Okay, thank you very much. If there are no further questions or comments, Dr. Wróblewski, would you like to say a few words to finish it?
Yes, thank you, Eduardo, for a very interesting lecture. I'm impressed with the chapter on machine learning. Okay.
Yeah, this is an area, I am also very interested. One of the reasons, because if you have a good student with a computer, you can collaborate with another university or another and put a lot of data. So it's something that appears to be very popular. And again, for example, my son that works. Indeed, he was the one that ran the models for me. He used machine learning from a company that has nothing with engines. It's for, to be honest, to be selling beers. So the company is Heineken, and we receive information when, where, and when the more beers are sold, and they use the model to predict how to deliver the beers, how much they have, and very similar machine learning tool was used for the engine. So it's very interesting. We are working now not only with my son, but I have a Valencia student collaborate with OEMs here in Brazil. Probably we are due to publish more things in the future on that. It's very powerful and relatively cheap. If you have the data, you can make predictions.
Very interesting connection of the beer production and engine performance. And that's an amazing thing. Yeah, but this is it. So, Dr. Wróblewski, are we finishing off? Yeah.
Myślę, że możemy kończyć już.
So thank you very much for this. It was really a pleasure and a very informative and interesting lecture. I hope we will be in touch. And as I understand, you have promised to distribute the PDF.
Yes, I will send a PDF to Piotr.
Okay,
and,
so
the ones interested, please ask him or someone to put in a public. I also understand that you recorded this presentation, so later on I would like to see my mistakes.
Okay. Okay, so Merry Christmas to you and a Happy New Year.
The same for you, for the audience, and for the family. Happy New Year, Merry Christmas.
Thank you.
Bye-bye.
Thank you very much.